Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To the panel on the future of supercomputing, of high-performance computing. We've got 4 speakers today. I'm going to go ahead and let each of them introduce themselves. The format we're going to have is that each of us is going to give about a 10 to 15 minute talk, and then the rest of the time is going to be devoted to questions and answers. So without further ado, I'm going to let Fran Berman go first, and take it away.
Okay. Thank you. Thanks for inviting me. This has been great. I'm going to introduce myself, but I'm going to tell you that the hat in which I'm going to give this talk is not as a professor, but as a director, because I think that's where we wanted to go with this. So Dan Fay started out by asking us some questions to frame our remarks. And they're basically in kind of 2 categories. What are the issues for today, and what are the issues for the next 5 to 10 years? So I'm actually going to try to answer those questions from the perspective of SDSC, San Diego Supercomputer Center. So let us start in the Bible. In the beginning, there was the Branscombe Pyramid. And a lot of what we have come to expect from the supercomputer centers really grew out of the paradigm of the Branscombe Pyramid, with the notion of workstations and mid-range processors, center supercomputers, and at the top would be teraflop class. This is circa 1993. Scientific computing was thought at that point to really sort of go more towards the top. So really the idea was that scientific codes were really handled at the top of the Branscombe Pyramid. And the key function of the supercomputer centers were really to provide facilities over and above what could be found in the typical campus and lab environment. Well, today's version of the Branscombe Pyramid, if it's even relevant, is quite different. First of all, we have amazing numbers of personal devices. Somebody was telling me that there's 1.7 billion cell phones, and who knows how many laptops, maybe you all know, but certainly quite a few. A lot of mid-range and large-scale clusters and parallel machines, a lot of teraflop class computers at university campuses, regional facilities, centers, and a very few 100-plus teraflop class machines. These days, scientific computing happens everywhere. And it happens as an integrative activity really throughout that whole pyramid. And in some sense, nobody sits in our machine room and programs DataStar or accesses the data collections on storage. Everybody does it remotely through their local environment. So the integration between the local environment and the high-end environment turns out to be really important. Now, it turns out that there's really more to the story than the Branscombe Pyramid told. And the fact is the Branscombe Pyramid really worried about kind of compute. So you sort of think about more flops, but today's scientists and engineers are really worried about kind of data as well. So it's not just more flops, it's more bytes. And the fact is, you know, these days you can kind of think about the landscape as, in some very simplistic way, occupying those 4 quadrants, where in some sense we have, you know, small to reasonable compute and small to reasonable data at our home, our lab, our campus, our desktop, our PDA, our cell phone, whatever. That we do have traditional high-performance computing environments, but we have a whole new set of environments around data-oriented science and engineering, where you have large-scale data collections, small to medium compute, large-scale data collections, large-scale simulation, etc. If you look today at where scientific applications run, and this is the first future of scientific computing, you see some more delineation. The data management environment, where would the protein data bank live? You know, 150,000 hits per day. That would live in that corner there, because lots of scientists take the information they get from the protein data bank, and then use it on their desktop or their laptop or on small-scale clusters to do the kinds of things they want. We have the extreme I/O environment, where you're really trading around data collections the size or more of the Library of Congress, and you see things there. And what we find is that all over, there's lots of scientific applications, and they fall all over kind of this new grid. Some of them lend themselves to grid computing. You can distribute them. They're latency tolerant. You know, sometimes it's like going out to Saturn to get your data, and that's okay. Some of them are not latency tolerant, and they can't be efficiently targeted to the grid. Some of them we haven't yet efficiently targeted to the grid, but they could lend themselves. So the idea is really not to address one kind of application, but to really address the spectrum of application with today's facilities. So that I wanted to sort of start talking about SDSC just a little bit to give you some context for these remarks. SDSC has really evolved over the last 20 years as supercomputer centers have had to evolve to really address today's problems. So if your goal is always to do something over and above what could be done in the ordinary campus, department, laboratory, home environment, you have to change with the times. This is the internet era. And so what we do is we provide a wide variety of facilities, from data-oriented HPC and storage to over 70 different community databases and data collections, data-oriented scientific applications, and data-oriented software and services. And what you find is that the supercomputer centers today fall in that gap between professorware that we've all developed in our labs and commercial software, where we really don't have the person power or the time to kind of robustify and really document and really make things a rock solid like you can when you have a real market for that. There's lots of projects associated with it, from earthquake engineering to life sciences to geosciences, et cetera, and of course grid computing. So that gives you a little bit of context about where we are at SDSC. Of course, I'm happy to talk about it for hours if you're interested. And I wanted to answer Dan's questions, which is, what are today's challenges for SDSC? What are tomorrow's challenges for SDSC? I do want to point out that it looks like that almost all the time in San Diego, so in case any of you were wondering. Today's challenges for SDSC are really integration and coordination. So when I think about today's computer, it isn't just a CPU. It's a coordinated aggregate of all kinds of compute, data, storage, network, software, internet. You know, I want it to connect up to the world's most powerful telescopes. I want it to connect up to my little pocket PDB. I want it to connect up to visualization and to the internet. And so the real issue for today's computation isn't just, is the hardware design fast enough, you know, capable enough, et cetera. It's, are we integrating things at a level that's really helpful for our users? So for us, today's real issues are all around sort of integration and coordination. Those give us a lot of different challenges. Greg just very eloquently, I think, talked about the notebook project. That's something we've been doing with Microsoft among many other projects that we're doing, and the idea is to provide a digital laboratory notebook environment for users. These things have to be flexible. They have to provide things that are very usable. And the idea is to integrate resources at all scales. So you can go from your notebook to a large-scale simulation, to a large-scale database, to you know, a collaborative environment, et cetera. One of the next problems that we have today in the supercomputer I think about is incorporating the ilities. Scalability, predictability, usability, interoperability, flexibility, reliability, et cetera. In today's world, with our users, and we have, you know, thousands of users, which come not just to use the data-oriented high-performance computers, but to use the biology workbench and to use the different data collections and to use the various and other things, they want predictability. And with all kinds of technical things, there's always the interval, the range in which you can expect behavior. Users don't like things like the graph down at the bottom with the black part. They don't want to know that things are going to go pretty well, and occasionally things will take 4 days to happen. Okay, what they really would like to know is perhaps that the interval where they can expect the behavior of the technologies is to be much tighter, so they can really understand within what realm and do their own planning. They also don't want to come and find pages not found. They don't want to see spaghetti code. You know, they really want to see something that they find usable, and that's really important for today's national centers because we're really in the service business these days more than ever before with our users. Another area where they would really like to see us achieve, and we would like to see this as well, is reliability. And today at SDSC, we're very, very interested in data preservation, data management, data curation, etc. One of the things that we have to do is adapt to a whole new model. So, you know, it's very well and good if you can't access your data for a day or two or 10 minutes or whatever, that's annoying. If we lose your data, that's unacceptable. It's an unacceptable mode of failure. So one of the things that we've done for the very valuable data collections we preserve, and some of those are for folks like the Library of Congress and the National Archives, is we've had to look at a variety of different approaches, from replication to heterogeneity to all kinds of things to address and mitigate some of the problems that can go wrong, anything from a corrupted file to a meteor falling on SDSC, which would not be good. So the idea is to really look at all these kinds of issues, including business models, because when you make replicants, it costs money for extreme data curation. Okay, so I thought I would briefly talk about tomorrow's challenges for SDSC, 5 to 10 years from now. First of all, and many of us, including myself, have come through grid computing, what we'd really like is adaptivity. We would really like our technology to take care of the problem for us. And still to this day, Rich Wolski did a very interesting experiment back in supercomputing 1999, and still to this day, it's one of the most creative applications I've seen and one of the best examples of adaptivity. Rich sort of ran Ramsey number problem. That's the party problem. All of us, you know, for any two of us, we either know each other or we don't, and we're looking for cliques of a particular size. And the size of those cliques are the Ramsey numbers, essentially. So the idea was that Rich ran on everything that was available at supercomputing, essentially. NT, Unix, Legion, Globus, Condor, Java, NetSolve. He saw different kinds of performances from all of the different infrastructures and software packages with the Ramsey number problem, which was not embarrassingly parallel, by the way, but he got aggregate performance, that was the black thing at the top, by adapting well. These are the kinds of codes that we'll be seeing in the next 5 to 10 years. I want to just throw it out there and get something with the kind of library I want, which will give me the best performance, etc. And this is a real source of research problem, to do this with security, to get the right performance models, to understand the right statistical models that apply to this, to understand programming environments for this, etc., is a really difficult problem. Another problem I think we'll be seeing in spades in 5 to 10 years is what I think of as the dynamics of sharing. Once we build these beautiful resources and we all want to use them, some of the most difficult issues will not be the technical issues, but the issues of group dynamics. Policy, distribution of control, social issues. You know, why aren't we all killing each other out there on the freeway? Well, somebody sat down, a number of people sat down and created a set of rules called the Motor Vehicle Code, so ostensibly we wouldn't bump into each other so much. We're going to have a motor vehicle code for our distributed technologies. Some of the most interesting innovation that comes in the dynamics of sharing is coming from the commercial world right now. I ripped this off from my son, who is more than happy to give me a little screenshot of his guy going out and killing things. I told him, give me something where things blew up a lot, so stay tuned. And the interesting thing about this game that he was playing, to me, is he's doing essentially collaboration down at the bottom. He's dealing with his own personal little database of tools and spells and wizards and, you know, stuff like that. And they're doing this in a very, you know, exciting, compelling visual environment. Now, You know, many of us go home and our kids are playing just these kinds of games. And if you think about, you know, how much more exciting our science and engineering environments would be if we had collaboration, easy collaboration environments like this. Of course, in group entertainment, you often see game masters to make sure that the interval of appropriate behavior is within something that's reasonable. So again, the social issues are there. We see shopping as a group activity, we see communication as a group activity, et cetera, these days. And so I think in the next 5 or 10 years, we're going to be seeing a very interesting sort of meeting of what's happening in the academic space and what's happening in the commercial space. The last but not least, this is sort of a heads up for us all. By the time we're all in retirement, the next generation will have taken over. And they're our next generation of scientists, of consumers, of leaders, and they're starting out from a really different place than we are. And I think as educators, as researchers, as you know, industrial folks, there's a lot to be learned from just where our kids are at these days. If you sort of look at what our kids are going to college without ever taking their first calculus or differential equations class, they assume that everything is available online and it's free. They assume that none of the resources have to be where they are. They assume that they can communicate with anyone, anywhere, anytime. They assume that they can adapt to things in real time. And they're assuming that, and they're coming there with some rudimentary level of business model. They've all been playing the sim games. They know when you build a roller coaster, when you need extra cleanup guys because it's not working so well, you know, all of those kinds of things. And this is where they're starting. So, you know, I think given that that's the baseline, I think we should all expect traditional ways of doing things to change. And I think in the next 5 or 10 years, we should be heads up on this. That, I thank you. You have to go.
Is this on? Okay, great. So I'm Jay Boisseau. I'm the director of the Texas Advanced Computing Center at the University of Texas. I'll try to keep this brief. I want to make sure there's lots of time for questions because, in fact, as you saw from Fran's presentation and you'll hear from mine, we come from pretty different backgrounds than most traditional Microsoft users. And it's very interesting to us to see this movement into the technical computing marketplace by Microsoft. And I hope that we give you some context for the way that we see the world, which even in clusters in HPC is not necessarily exactly the way Microsoft sees it. If you came to the brown bag lunch today, you saw Kirill's excellent presentation, but it still comes from a different perspective sometimes than the way we see things. So 2 points of context here. Much computational science requires large-scale computing. It's not the case that all of it does, but there are certainly advantages to large-scale computing of the kind that Fran's Center and my center and Dave Lithka's center support. Some of the obvious things, and hopefully you're somewhat familiar with large-scale computing and the role in computational science, but just to recap, certainly bigger problems you can solve for larger domains and or higher resolution. Certainly you can run more cases with large-scale computing resources. This may be important in exploring parameter space and statistical modeling, etc. It also, of course, the obvious one is faster time to solution. And if you think about it, many of the problems in nature require one or more of these 3 characteristics. And an example right now that's particularly relevant to my home state is severe weather forecasting, in which case they actually need large-scale computing for all 3 of those reasons, to run lots of models that are very highly resolved to try to figure out whether this hurricane is going to hit Texas or Mexico. The other point of context here is that computational science has a growing scope, and this has actually been an interesting conversation I've been having with people as I move into the life sciences. Everybody has pretty much accepted for the last 10 or so years that computational science is this sort of third modality of science, along with theory and experiment or observation. And since I'm an astronomer, most of our experiments are observations. But most people have accepted that computational science is this third modality, but mostly what they meant by this was simulation-oriented computational science, hypothesis-driven computational science, the kind of science in which you develop an application based on your knowledge of the underlying physics and mathematics, and you attempt to model nature. And there's this new type of modality for computational science, is informatics or data-driven science. And it's really got some very different and interesting characteristics, and we're seeing that become a larger and larger percentage. It's by no means the majority of our usage at our center yet, but it's definitely a very significant percentage of the usage of the resources. And so we have to account for that as well when we look at the future of scientific computing, because that's definitely the direction things are going. So the key technical issues faced by TAC, they're very similar to the ones that face Dave's center or Fran's center. I put the key technical issues in the middle. I couldn't help but emphasize that the key issue overall probably really is this funding issue. And you heard enough about that at various presentations here at the meeting, but it's really a critical issue in the future of scientific computing and the future of academic research overall. But getting to the actual point of the question Dan wanted us to answer, the key technical issues. These include a lot of things, and I hope that a lot of this will get discussed in the Q&A session, because there's no way that I could have listed every key technical issue that we face, but we do face these and we do address them. Some of the major ones that are facing us is the difficulty of parallel programming at very large scales. This is actually more difficult than it sounds. When we teach people how to develop parallel programs, a lot of them think MPI is pretty complex, and some of them think they can get their hands around it. But the problem is these systems are not well-balanced systems. It's very difficult to make the application scale to very large processor counts. And so that's actually still a key issue facing centers that are trying to support very large-scale computation. If you heard Kirill's talk today, you heard that in the industry space, a lot of applications scale to 8, 16, maybe 32-way. And that's all fine and good, but in the space that we're in, we're trying to get people to scale applications to hundreds of processors and potentially thousands of processors. And that's a whole different challenge. Just knowing the syntax of the parallel programming technologies is not sufficient to get your application to scale and really address those large-scale problems. Complexity of Linux cluster system management at large scales. I'm sure the Windows team probably loves me to see this bullet up there. That's a real pain in the wazoo, trying to manage these very large-scale Linux clusters. I don't know how many times I've been told we couldn't install package X because we didn't have the right kernel version. And we couldn't update the kernel version because it would break our software management kit for managing this 512-node cluster, et cetera. So that's actually a big issue facing us, and one reason we're very happy to see the Microsoft team enter the HPC market. I/O performance. Fran talked about the emergence of data-oriented applications and data-intensive applications. One of the things that people in our community tend to sort of ignore until they can't ignore it anymore is the I/O performance. Everybody loves touting their sexy flops benchmarks and how fast their application is. But of course, they time it after they've read in all the data, and they stop the timer before they write out all the data. Now it's getting to the point where they can't do that anymore, and instead they complain to us about how fast or slow our I/O systems are. So we're spending a lot of energy in that. Sustained flops performance is actually a real critical issue. Everybody touts the teraflops capabilities of PCs, and lately I've been seeing more and more about how the Xbox is a teraflops gaming system, and the other one, the PlayStation 3, is a 2 teraflops gaming system, and those numbers are absolutely meaningless. No one is ever going to sustain even 10% of the performance on that for any length of time on any real code. Those are the theoretical peak capabilities caused by adding special operations the GPUs can execute, and special operations these SPE units on the cell processor can execute, to the much smaller but more general purpose operations that the CPUs can sustain. It turns out it's very difficult to get sustained flops performance, especially for scientific computing codes, because if you think about it, we're not the largest part of the industry, and the processors are generally not developed with streaming large amounts of data from memory into the CPUs and producing lots of adds and mults. But that's exactly what we need. I should also add here that in addition to these technical issues, a key operational issue is the power and cooling, and also the space for very large-scale systems. So in an interesting change in dynamics in academic industry collaboration. Excuse me, it used to be the case when I was actually at SDSC that these companies wanted to buy cycles from us because the cost of buying their own Cray supercomputer was so large that they couldn't afford it, so they'd buy a piece of our Cray. Then with the advent of clusters, they figured, oh, well, we don't need to do that. We can buy a much smaller scale system and we can operate it ourselves. Now it turns out when the oil companies want to run a very big reservoir simulation, something that requires 1,000 processors, now there's actually interest in some of them in coming back to the centers, and it's not because of the cost of the Cray supercomputer, it's because of the cost of the infrastructure to support these very large-scale systems that require lots of power and lots of cooling. So the challenges that we see in the next 5 to 10 years, and there are challenges facing us now, developing scalable applications on commodity-based systems. More and more, as you saw in the lunch session, if you were at that, clusters are beginning to dominate the list of most powerful computing systems. They're certainly not perfect solutions for all applications, but they're certainly very good price performance solutions for many applications. But as I mentioned, it's very difficult developing these scalable applications for them, and that's whether you measure it in terms of high sustained performance per dollar, per watt, or per square foot. And there's difficulties with each of those. The complexity of the programming environments is high. Not everybody becomes a master of MPI programming. There are certainly performance issues, and these are both the theoretical performance issues of trying to write scalable applications, and then the performance issues caused by imbalances in these system architectures. The processors are faster than the memories are faster than the interconnects, and that further limits the actual sustained performance you're going to get. This results in sustained performance being a very small percentage of peak performance, and it's getting worse, not better, with the complexity of these architectures for scientific computing. Some other challenges here. Data analysis and visualization. I have a strong visualization group at my center, and I really feel for these guys sometimes because visualization is often treated as just sort of a service that should just be there for the brilliant physicists that are solving the big high-energy physics problems or the astronomers solving the cosmology problems. But for visualization, they think it should be as easy as putting a CD in the system, installing the package, ingesting the data, and out comes this very informative visualization that gives you all the knowledge you could have needed to know from your output. And in some ways, it's been like that in the simulation-based modality of computational science. The hard work has been incorporating the physics into the application, and people have written some very good visualization applications to look at that kind of data, time series, gridded data. But it's becoming much more challenging to analyze data in this new data-oriented world in which you're starting with massive amounts of data instead of with the underlying physical knowledge. So there are some new challenges arising in data analysis and in visualization in particular. The data sizes are growing exponentially, not just because the system sizes are growing exponentially. And the system sizes, you have to remember, are not just a function of Moore's law and CPU power, but also of the interconnects for which you can now couple more of these processors together, but also of the ability of instruments and sensors to collect data. So we really think there are a lot of challenges here. We recognize that sometimes it's going to be better to move the analysis closer to the data rather than moving the data to the analysis system. And so we have to look at things in that area. Fran already talked about some of the data management issues, and I've alluded to those as well. And Fran also talked about integration of things. And the NSF buzzword for this is cyber infrastructure. So I'm not going to get too much into that since you've now heard a little bit about grid computing at the lunch session and a little bit about it from Fran's talk. But it's certainly a challenge to begin to integrate all of these resources because users are using all of these resources, but they're using them all manually and in steps and moving their data to each one and tracking their data and processes on each one. We really want it to be much more seamless. So the research problems, well, you can pretty much draw those out from the previous slides. I list some here, but there's an enormous number of research problems, which is why this funding shortage for academic research in computing is so important and so crucial that we get it addressed. And it ranges from scalable algorithms, which I've mentioned, to fault tolerance, so I guess it would be the ILITY would be the reliability that Fran was mentioning earlier. Many aspects of cyber infrastructure, of integrating these resources. It's not just about the United Devices computing style. It's not just about compute aggregation. It's about data aggregation. It's about workflow through the different steps you do. Improving sustained network bandwidth. If you came to Wolf's presentation the other night, several times he referenced the book, The World is Flat, and one of the big flatteners has been the ubiquity of high bandwidth networks. But in fact, they're not everywhere yet. The last loop is the issue for most people. So while we're deploying 10 gig E networks around the country, I'm pretty sure you don't have a 10 gig E network connection into your house. And even if you do, if you actually measure the percentage of sustained utilization of that, you'll see that it's very small. Large-scale visualization techniques, perception-based visualization techniques, actually understanding how evolution trained the eye and brain to work together and work to be able to analyze data more effectively and more quickly. I felt obligated to do a few predictions here since this was called the future of scientific computing, and I'm gambling that nobody's going to go back in 3 to 5 years or 10 years and actually check and then call me up and tell me where I was wrong. So I didn't mind actually putting some of these in the presentation. Certainly improved manageability of clusters. Microsoft is certainly going to help tremendously in this area, but over the next few years, I think you really will see people being able to manage their own clusters as opposed to acquiring lots of expertise in doing it. We really see remote visualization as well as computing emerging over the next few years. Network bandwidth, it's an interesting thing. Visualization is a compression step as well as an analysis step. So sending images is much less bandwidth intensive than sending the entire data. So as you generate these very large data sets, maybe you should do the analysis and the visualization where the data resides and then send the images, and we're actually doing that now. This is on my next to last slide, Marvin. We also expect a 10x increase in the number of parallel programmers, and I made that order of magnitude number up. Why? Because of the prevalence of multi-core chips. This is something I'm actually very excited about. No one will be able to buy a system soon that's not a multi-core chip. I think that when you look at Ars Technica and Tom's Hardware and you see this hacker community out there that tries to get every bit of performance and measure it on everything they can, this is very exciting. This is going to increase interest in parallel programming. And finally, a couple of more. We do see advances in, we do see cyber infrastructure eventually becoming seamless. It's certainly not there yet. There's a lot of grid computing projects out there, but I wouldn't pretend to tell you that any of them are seamless all the way down to the desktop for general purpose applications. And finally, we do think that large-scale centers' roles are still required for resources, but also for expertise. And then we think that's continuous, not just 5 to 10 years. But I don't really see that going away because the reality is for large-scale computing, it's getting more complex and more difficult in many ways. It's not necessarily getting easier at the very large scale. So I do see that role continuing. That's it.
3 slides. So I'm Dave Lifka. I'm the Director of High Performance Computing Systems and Innovative Computing at Cornell for the Computing and Information Science Department. That includes the Theory Center. So recently my role's been expanded, and actually a lot of things that I've been hoping would happen for about 10 years are starting to come together. So there's been a lot of talk the past few days about why can't we get computer science students interested anymore? What's the problem? And I think the problem is the teachers. We're not getting them excited about what the potential is. We're not telling them why computer science is a great field and it changes every day and that's exciting and that means you can participate in any area of research you want to if you understand the basic tools. The first class we teach them is how to write a program, and it's boring as hell. Right? So how do we change that? And so computing and information sciences is actually reaching out to other disciplines, and we're finding out they know more about algorithms in some cases than the computer scientists to solve their domain areas of expertise. And so I've been for 10 years wanting a system that a biologist could talk biology to and get an HPC answer without ever knowing what MPI was, without ever knowing what a teraflop was. And I think some of the things that are starting to happen today, and you've heard about from Microsoft, are making that nirvana a reality. Slow, baby steps, but important. The vision for Microsoft's HPC stack is that you'll have your own personal supercomputer. It'll replace your workstation with multi-core processing, with multi-processor systems under your desk, fitting in a shoebox. you're going to have a parallel computer on your desk. If you have to know how to use MPI or OpenMP to use it, it's going to fail. And we know that, we've heard all week, that if we're counting on gigaflop rates and things, or clock speeds, gigahertz rates and things like that to get us the performance, it's going to run out. So we have to think about concurrency and parallelism. And these are real challenges to us, to our community. Maybe our operating systems we're working with today, Windows included, aren't ready to handle that. Do we have highly concurrent operating systems? I would argue no. Who's going to fix that problem? I think we should be thinking about. These are real situations, real problems that are going to affect performance in the next 5 years. I think the biggest breakthroughs, the biggest potential breakthroughs in this area, in HPC, are going to come in two areas that you're probably not, maybe you're not expecting, but I think it's natural language processing and social aspects of computing. Studying how researchers want to use the computer, not how we computer scientists dictate they have to use the computer. And then it's our job as computer scientists to do that plumbing behind the scenes and make that reality happen. So an example, baby step. My mom goes on to Solomon Smith Barney at night and says, what's my portfolio worth today and what's my value at risk? That's probably running on a cluster. Does she know it? No, because if she did, she'd never touch it, right? But that's reality. That's HPC, and that's an area, that's a domain area of expertise. She knows, she understands her portfolio, and she wants an answer, and she wants it fast, really fast. So what about the biologist who wants to know what this protein looks like, or does it look like anything else? Shouldn't that come back in 2 seconds like it would on Google if you were looking for your favorite music CD? So that's the kind of thing we have to build in the next 5 to 10 years on changing platforms, on changing tools. And so I'm encouraged that companies like Microsoft are considering end-to-end software tools that give you integrated security and integrated development tools that let you build these things. You heard from Fran and Jay all the different intricacies and complicated components. You're going to see the same things on my next 2 slides. But what's going to glue all that together and make it easy for the biologist or for the physicist? If it's MPI, we're in deep trouble, folks. So we've really got to think about that. So this slide's going to look familiar because these are the problems. Data-intensive computing, we have 3 projects that we were funded by NSF last year to support. We're going to consume a teraflop of new data every day. We're working with Johannes Gehrke in computer science to figure out how we can make sense of that data in real time. How do you manage a pipeline like that? FedEx is part of that pipeline. How do you do that? That's a hard problem. Seamless computing is important. The computer, the parallel computer, has to become a tool. It has to speak your language, your domain language, not computer science. We heard someone complain that the systems are unreliable. What's going to happen when we add more complexity? It's going to get worse, not better. So I think of this idea of research domain theme packs. Much like, you want your screen, your windows to all have the same windows and the sounds just change accordingly, and you maybe use a foreign language. I want a biology theme pack so that I, as a biologist, can talk biology to the computer, and it understands what I'm asking when I talk about comparing 2 proteins, and I don't have to know anything more than that. I want that to get translated into something that does something real computationally and gives me a real answer. And that's a hard problem, but it's not, with natural language processing, it's not insurmountable. So we need to start thinking about those things. Seamless parallelism and concurrency. The OS has to have the concurrency and the parallelism baked in, and the apps there has to be tools to develop the apps to take advantage of it. So there's these exciting areas for computer scientists to do the plumbing and the glue behind the scenes to make these systems incredibly usable. Seamless interoperability. The whole world's not going to use Windows, and the whole world's certainly not going to use Linux. But I don't want to care. If I'm looking for data that's relevant to my research, I just want it to work, and I want it to plug into my app. And so, things like web services and XML and all these different things we hear about constantly, especially here, they're important pieces of the puzzle. So, last slide. So, how do we attract computer scientists, students to computer science? Those problems are exciting. Those are hard. Those are breakthroughs. Those are the problems that people are chomping at the bit for, and probably will fund you to do if you tie it to real research. So how do you make their requirements a reality? That's the key. And there's tons of challenges and opportunities here. There's many that I haven't mentioned that I'm sure are going through your heads right now. And so it's all the way from plumbing, people that write programs to glue things together and make them work behind the scenes, to high-level research, the natural language processing, and all those types of things. And change is exciting. And talk about a dynamic career. Every single day you go into your office, there's some piece of press that comes out that's going to really affect what happens and how you get your work done in computer science. That's exciting, and I think students aren't getting that message enough. So with that, I'll just turn it over to Marvin, and we'll move on. Thank you.
Okay, I'm software architect for the High Performance Computing Group in Windows Server, and unlike the three people who were coming from a supercomputer background, I'm going to be coming from the bottom up. So this is Attack of the Killer Micros here. I'm going to focus on a low-level issue and a high-level issue for my discussion of the future. Let me start out. If you went to Carol's brown bag, you'll recognize this slide, right? What we think the very near future is these boxes here on the right. $3,600 buys you the same thing that $40 million bought you in 1991, right? Personal supercomputing. Or, let's see how this go. You know, to more specific, you can imagine that soon a molecular biologist is going to have this kind of a workstation. It'll be a turnkey system. It'll cost $10,000, which is interesting because that's what industry is willing to pay for an engineer or scientist on the desk. So that's why we think this is going to move in and replace all the technical workstations. It'll come prepackaged with all your applications you want. It'll be more interactive than batch. It'll run things like workflows. So that's the near future. It's interesting to think about where that trend is going, right? You know, it's already been mentioned that, you know, we get teraflop numbers out of these new chips here, right? In theory, the IBM cell processor will give you 256 gigaflops today, and so in theory, a 4-node personal cluster is a teraflops, right? So that $3,600 system I was talking about now becomes a teraflop, right? Now, of course, that's a hopelessly unbalanced system, and no one knows how to program it, so that's all a lie. But it's interesting to speculate where the hardware is going to take us in terms of what I can put on my desk for $10,000. Or $5,000, right? Same thing with Intel, hundreds of cores on a chip by 2015, and so you get to similar kinds of numbers, right? 4 cores per teraflop, you're talking about 25 teraflop machines. Now, will we really get there? I don't know, but I think this is a key trend here, because what it's leading us to, one of the trends that we're seeing here is this trend that's been going on for 40 years. Mainframes got replaced by mini computers, which got replaced by personal workstations and departmental servers. And we think the next step is going to be grids of personal and departmental clusters. So that's one trend for the future of HPC. But there's other things going on, and there's, in fact, a countervailing trend that I'm going to bring up shortly that leads to an interesting tension. But let me first stop out here and sort of focus on today, tomorrow, and the future. If you look at today for HPC, and I'm going to use cluster computing as being sort of the common case for HPC. What do you have? You have departmental clusters. These are IT-owned. They're large clusters because everybody's pooling their resources to deal with the complexity and put it all in one system admin's job. Users submit batch jobs via scripts. It's mostly in-house applications and ISV applications, and it's based on this assembly language thing called MPI, right? Stone Age messaging. What are the issues? Well, scheduling the focus here is scheduling multiple users' applications onto scarce compute cycles, and it's all about cluster systems administration. That's the #1 pain point that you'll hear about if you go actually talk to people who do this stuff, right? In the near future, personal to work group clusters, right? So we see this emerging scenario where clusters are prepackaged. Desktop HPC applications can now start pushing their computation into the cluster on the back end transparently. You're talking about desktop development tools instead of just MPI programming for the batch thing. The focus now becomes interactive applications, and it's about compute grids and distributed systems management. That's sort of where the near future that we see the issues going. But in the long term, we don't think it's compute, it's data, right? You've heard this from everybody else. We see the same thing here, right? The future scenario is people are starting to do multiple simulations. They're integrating data sources from clinical trials or from CERN and so forth into the seamless applications workflow. You're starting to get network topology and latency awareness for the optimal distribution of this computation, and you're seeing structured data. The key thing is that data here, right? It's data-centric in its whole system workflows, and it's about data grids. Just to give you the example here that we got from one customer was there's a party interested in taking a patient who needs surgery, doing in real time an MRI of this person, getting that data, doing all the transformations in order to put it into a system where they can simulate that person, show to the surgeon the simulation of that person, allow that surgeon to virtually do their surgery and see what the best outcomes would be of different choices, take that simulation and the output, pipe it to the OR, and show it to the surgeon while he's doing his surgery. That's the future, and it's data-centric, right? The thing that stays around is the data, not the various computations that danced around and transformed that data. So that's our today, tomorrow, and the long term. But let me get back to a trend that is going to countervail the first one I mentioned, which is this attack of the killer personal micros, right? And that's data. The data sizes are huge, right? This is just to give you some sense of stuff, right? We all know about CERN and the fact that they're going to be generating a terabyte per second of data. But even just in the more mundane worlds where you're simulating automobiles or airplanes and so forth, you're talking today about tens to hundreds of gigabytes per simulation, and tomorrow you're talking about tens to hundreds of terabytes per simulation, and they want to keep thousands of them, right? So we're talking about petabytes to exabytes of data. Now the question here is, how do I move that stuff around and what do I do with it, right? One thing that you hear from CERN, for example, is, well, we're going to send this over these amazing lambda rail systems all over the world on the network. If you're in industry, as compared to in a subsidized academic setting or a government setting where you get those 600 gigabit channels for free, this stuff is not cheap. If you look at the cost of moving a terabyte, this is a slide courtesy of Jim Gray, and ask how would I move a terabyte across the country, you get some interesting numbers here. And to keep this short, the key thing here is that FedEx number. The only thing that's cost effective really is to move the data by FedEx. Now, I gave this slide at a talk to the National Labs IT conference, and sure enough, a couple of physicists got up and said, we did the calculations, and the network is cheap enough, and this is all hogwash. And then I had 10 different IT people from the various national labs come up to me and afterwards and said, we ship it by FedEx. So in the long run, you know, we see lots of high-speed data of internet connections for sure, but at least in the next 10 years for industry, we see this challenge. It's expensive. It's $100 per month per megabyte per second, just for the basic pipe. And so that's a challenge. Now, what does this mean? Well, if you look at the topology that you'd wanted to build as a distributed systems person for HPC, you end up with this islands of connectivity design. Meaning you're going to see clusters out there. You're going to see data centers of the kind that you just heard talked about by the 3 previous speakers. You're going to see personal clusters. You're going to see data warehouses that are going to store these petabytes and exabytes of data. The only way to move that data among all of these things is through some kind of high-speed interconnectivity. And then there's this interesting question of how do I get to the other places around the world. It may be FedEx. On the other hand, as Gordon Bell pointed out to me recently, moving a petabyte per week means shipping 1,000 disks per week. So maybe that's not so good either. But there's a fundamental tension in here, right? I've talked about 2 trends here that countervail each other. On the one hand, I've argued that for a variety of reasons, we're going to see personal clusters. And we strongly believe that because it's all the reasons why PCs dominated mainframes. And yet, large data, and especially the analysis of that data, tends to favor aggregation, data warehouses, so that I can do efficient analysis. And so the question is, how do these trends relate to each other? Are we going to see this model? Are we going to see it all collapse into one big data center? Will we see it dispersed somehow? That's an interesting question where there's still open research to be done. Just to make the point more clear about the data analysis, if you look at the way people today do data analysis, they tend to do it as I show up here. They keep the data in flat files, and for every question they have, they write a C program or a Perl program that runs over these thousands of files and gigabytes to terabytes of data. And the problems with that is, well, it's kind of tedious to write a C program for each one of these things, and basically scientists are reinventing the last 40 years of database indexing and query technology. And furthermore, they're copying that data from the file system to their program every time they do it. People like Jim Gray have shown that if you throw it all into a big relational data warehouse, then in fact you can get speed-ups of 2 orders of magnitude or so compared to this traditional approach if you do it that way, right? And you can do things like write application and domain-specific stored procedures that greatly simplify how you do things even on a domain-specific basis. So this is part of why there's this question, how much are we going to have aggregation down into potentially just giant data warehouses with computing all inside of that, and maybe clusters or something dancing around it to do various simulations, and how much are we going to see this dispersal onto people's desktops? We believe both are going to happen, but the exact mix of this thing, I think, is one of the interesting questions of the next 10 years. Well, so that was the low-level issue, right? So is that the end of the story? Well, really, the much more important issue is the fact that everything I've shown you is still way too complex. And that line on the red really says it all there. The 2004 NAS supercomputing report said that about 35 computational scientists are going to be graduated in the next year. So think about this. Our entire industry is starting to use HPC in order to do everything, and there's going to be 35 people that know how to do it. Now, what do I mean by those 35 people? It's the people that can deal with all the issues I've shown down here. Parallel application development. They're going to understand chip level, node level, cluster level, LAN grid level, WAN level parallelism. They're going to understand OpenMP, MPI, HPF, global arrays, component architectures, performance tuning, debugging, all this stuff. That's, you know, just so they can write these applications, right? On the system side, they'll have to understand security, system management, directory services, storage management. They're going to have to understand how to manage thousands of experiments, deal with the provenance of the data and so forth, and version management. Oh, and by the way, there's this little thing over there called domain science, which is the only thing that they're actually supposed to be doing. Right? So this is the challenge. This, to me, is the fundamental challenge of the next 10 years. Don't solve that, and you lose the opportunity that cheap supercomputing is offering us. So I claim this leads us into the direction of something like this, where we have to separate out the domain scientist from the computer scientist and somehow layer this thing so that a domain scientist knows about, or sorry, a computer scientist worries about all these things like parallel and distributed file systems, relational data warehouses, and so forth. In the middle is somebody who can cross that boundary and understand some amount of parallel domain application development, but doesn't worry about distributed file systems and things like that. And down the domain scientist is somebody who doesn't think about most of that at all. They think in terms of interactive scientific workflows integrated with collaboration-enhanced office automation tools. So to give a specific example, the domain scientist needs to be working in a world where they think of, I'm going to write a paper with something like Word. I'm going to collaborate with my co-authors using some kind of a collaboration tool like NetMeeting. I'll record my experimental data with something like Excel because I grew up with something like Excel. And I'll share my papers with something like SharePoint. And each individual experiment that's in one of those Excel cells, when I click on that thing, I'm going to get a workflow orchestrator that gives me a visual programming language to specify what happened and what I could do in order to change it. And if I want to analyze the data, that same Excel spreadsheet is going to transparently let me get down to my SQL data warehouse. So he doesn't think about anything in the way of computer scientists. For him, it's all office automation. Now, surprise, surprise, that's the view from Microsoft because we have a lot of expertise there, and that's where we think it's going to go. But I think we have to get to that level in order to allow the 90% of domain scientists who don't have the time to learn computer science to actually move forward. I'm going to end here. In fact, I'm going to just leave this up and stop, and we'll go to questions now. I've been asked to remind you that if you want to ask a question, raise your hand, and they'll bring you a microphone so that we can get it all onto the tape. So do you guys want to come up, and we'll answer questions?
Dan Pitt, Santa Clara. So you just touched on a point that Fran had brought up earlier, which is that supercomputing, even the centers as we know them, offer a service to many other disciplines, and it's the people in those disciplinary domains that understand the nature of the problem and increasingly understand the computational requirements and the algorithms maybe even better than the pure computational scientists. What is this, where is this really leading us in terms of the nature of being a domain scientist versus a computational scientist?
that's a really valid question. What we've done at Cornell to sort of address this situation is we've created what we call service units. And the reason for that is that the domain scientists don't want to talk to someone who doesn't understand something about their research. They don't have time for it. And the computer scientists, pure computer scientists, can't really, systems people can't really understand that either. So you need this special person in the middle, the computational scientist, that can sort of bridge that gap. And our service units that we've designed have been designed on purpose to bridge that gap. So we have two that have a big head of steam going right now. There's this computational biology service unit that reaches out to bioinformatics people all over campus. And they've built like websites where you can just type your email address in, upload the protein you want to run blasts on or whatever, or the comparison you want to run blasts on, and then you get your answers emailed to you. And so they listened to the problem, they listened to what they wanted, and they built the tool with the systems people and delivered a working solution. There's much more than that. The other one is the eScience service unit, which Johannes Gerk is in the back. Raise your hand, Johannes. Anyway, he's leading that effort, and that's because there's this data requirement that you've heard so much about. You need people that can understand how to take these piles of data in and make real sense of it quickly, design schemas, and show through this chain to get the domain scientists the information, the answers quickly. Those are only two ideas. I think it's a good model. We've had a huge increase in the number of users because we're providing that extra layer in certain areas. And so if you have other ideas of service units that you think would be useful, I'd really like to talk to you afterwards.
I think that's a really good question. You know, I think the issue is that everybody's first preference is to do things in their home environment. You know, what you really want to do is work on your machine in your lab, deal with your data, you know, put your jokes on the side of your desktop, etc. And I think the issue is what happens when you hit the boundary of your home environment. What happens when you need more system administration or reliability than you can provide at your own laboratory? What happens when you need to deal with a community database rather than an individual database? What happens when you have to run a 3D simulation rather than a 2D simulation, and it would take, 49 years on your cluster in your lab? And so what we find is that the people who exceed the boundaries, the comfort boundaries of their home environment are the people that we see most often at the center. And many of those are really interested in getting the last possible bit of performance they can because these are shared facilities and it's really important to use them as well as possible. So we find that a lot of the domain scientists have, at least a rudimentary knowledge of some of the computer science issues associated with it because they've had to in order to get good performance. Now, as their home environment becomes more capable, our job will always be to provide something that exceeds what they can find in their home environment. And in fact, that has changed over time. As we see more capable computation facilities in the real world and applications and tools that they can use, it changes the nature of what we do, but it doesn't sort of change our role. That's the experience that we've had.
I'll just add one brief thing. I believe what you have to do is strip away as much of the computer science as possible from what the domain scientist has to know. So the domain scientist is going to have to know how to program to a certain level, right? And an interesting experience I've had in talking with customers is a lot of people are perfectly happy to say write up a Fortran description of an algorithm. Where it gets painful is then parallelizing it, because the parallelizing has nothing to do with the domain science. In fact, it has nothing to do with the numerical aspects of it really, right? And so stripping that away would be the real challenge. If you could get rid of the concurrency, certainly you have to get rid of all the illities. They shouldn't have to think about reliability and all those things. That should just be there, right? It's the only way the domain scientists can spend more time working on their own things. Next question.
I just have to add something to the last part before I ask my question. I don't think it's the right thing to build such a strong separation, partly because the collaborations require deeper insight than just using a service. So I think Jay said something about that, but that's a debate for another time. The more important thing is you've talked about the funding problem. You've articulated the kind of organization that's required, that's been successfully built in several places. How do you justify building that capacity in an environment where the scientist gets rewarded by how good he does his science, how well he produces, and the service provider, so some of you are caught in between. How do you justify using money, if you can get it, to build that capacity? Because the university systems aren't always attuned to rewarding the people who are accelerating or amplifying with this sort of integrated science.
So, science is a collaborative process, but it's also a competitive process, of course. And when you operate a center like mine or Dave's or Fran's, one of the things you're trying to provide, and I think Fran mentioned this as one of her bullet points, is a capability that they do not have in their lab and do not have at their university in many cases. And so what you're trying to provide is not just a bunch of 8 processor clusters scattered around the campus, and maybe you can connect them all via some grid software so that you can run parameter sweep applications and so on, but some unique capabilities that are expensive. But the reality is, while we're moving to this data-driven world, you don't want your airplane that you travel home on designed via a data-driven application. You want a simulation-based application that simulates the physics as we understand it, and then eventually run through a virtual wind tunnel, and then eventually designed and built. So you've got to provide the very high-end computing capabilities for those folks, and you want to give them a competitive advantage as well as a scientific advantage. Likewise, you've got to provide the data-oriented computing capabilities and the visualization capabilities they don't have access to necessarily in their lab or in their department or even at their university. So I think that's how these universities justify funding for that. Now, I don't think any of the 3 of us would say our universities fund us well enough to do that. But on the other hand, each of our 3 universities has capabilities that greatly exceed the average capability of a university in the United States for high-end computational research, and hopefully each of our universities has researchers who are doing work and competing for work, writing proposals and competing for scientific work that our capabilities are enabling them to be very competitive and get the funding for it. So it's very crudely put, your VP for research may look at it as a return on investment.
So what do we need to be teaching our undergraduates so that we have a reasonable population of people who are interested in and well prepared for being computational scientists to support the kind of work that you do?
Well, let me just put in a plug. In my many, many years as a researcher, I've had the good fortune of doing research sort of both ways. I think of it, top down and bottom up in some sense. And, in some sense, sort of build it and they will come, creating a beautiful model of something and proving things about that model and really trying to understand what's going on with that model. You can have some very deep and fundamental results. We've also tried developing things from talking to users and trying to come up with what the real-world phenomenon were that they were experiencing. My work's in scheduling for those, grid scheduling and things like that for those of you that don't know adaptive computing. And when we started with the users, my experience was we got unbelievably exciting but messy real-world phenomenon. We didn't understand the statistical models behind it. It was clear that we weren't going for optimal, but we were going for good enough, and good enough was defined in different ways by different users at different times. And there was a lot of interesting research that came out of it. I would say in terms of teaching, giving students that kind of real-world experience to complement the more mathematical and very well-structured experiences gives them a broad spectrum of computer science experiences. I think that's really important myself.
So I had a traditional computer science education, and I think it wasn't until I got to Argonne as an intern that I realized how you use this stuff, and that was like 4 years too late. I mean, you had to really pick up the ball fast, and I think the same way we collaborate with domain researchers today is we should be looking for examples of the things we're helping them with and making sure we're teaching them at least at a building block level to the computer science students early on. Not only will it make them more prepared for what's going to be required of them when they get a job, but it'll make it more exciting. They'll instantly get an idea of how this is going to affect society or make a difference. When you go into biology or you go into medicine, you think I'm going to cure cancer or I'm going to do something great. What do you think when you take CS 101? You know, that's the question. So how do you impress upon them the potential of that, what that CS 101 is going to lead to?
I was just telling Jay that when you take CS1, you think, I'm going to kill things.
Several of you mentioned that operation support, network management, service management is going to be a big issue. In the telecommunications industry, it requires complex software systems even to do the very primitive kind of operation support that we have today. Your systems are far more complex. So my question is, who's going to build these operation support systems for you? In many cases, the protocols used by the network management and operation support systems limit or govern the rate at which you can evolve these systems. So where's the intellectual leadership coming from in defining the architecture of the operation support systems for this network of the future?
So, you know, I think that's a really interesting question, and it's a really important question for our discipline. And I think that in some sense we have to bootstrap. I think that we need a lot of examples and experience of things to try, you know, to see how to deal with the kinds of complex systems we have. On the other hand, you know, 1,000 points of light does not a single beam make. So on the other hand, I think we also have to try to use economies of scale to create the kind of systems that we need. Now the problem with these sort of large-scale complex systems dealing with networks, computers, you know, grid has been a very a term that's been around for a while and have been hyped a lot. The problem with building these kinds of systems is really getting enough experience to figure out what works, what doesn't, what should be centralized, what should be distributed, in what instances should we have distribution, centralization, security, performance, all those kinds of issues. My own feeling is that, and my observation is that when I see our communities on the cutting edge, things start with very specific scientific problems that they can solve. You know, how do I, you know, where do I place a, you know, nuclear facility? How do I, you know, break through and transfer information from inside to outside of the cell? And people build tools around this. And as people sort of share this kind of information, there's more and more clustering of more generic concepts that lots of communities can use with a base set of usage models. So then you have something that's more generic that provides kind of a common framework. It's that bootstrapping activity, I think, is the way we're going to get really usable, useful, complex systems. But I think just designing it from the beginning from the top down, or just letting everyone kind of flounder from the bottom up, all by themselves are not a good ways to go.
Just to add to that, I think that the key is industry partnerships with Microsoft, with companies like Microsoft, with IBM, other companies that are going to be driving the underlying systems, whether we like it or not. And what's going to drive that is what people are willing to pay for. So smart people migrate towards the best solutions and the ones that are the easiest to use. And so we have to make sure we track what these guys do. That's why we're here. And it's going to become increasingly important. You've already seen this sort of standardization. Everything's going towards, you know, x86 towards processing, software standard. Everything's becoming standard. So how do we influence that? How do we work with industry partners to make it easier and easier to manage it? How do we get the issues to them so they know what they have to watch out for?
I echo exactly what Dave said on that, and I think every week or every other week a different vendor comes into the center specifically to showcase their technology and to ask how it could be used in high-end computing. And in one case 3 weeks ago, they must have grilled us for an hour asking about aspects of the applications that we have, applications across the board, what their requirements were for latency, for bandwidth, for fault tolerance, et cetera. So we have a lot of academic industry discussions when you run these kinds of centers and you're dependent on these industry partnerships. There's a lot of discussions that lead towards how to use their current generation of products and what requirements you have for the next generation. And that's not just technical requirements, but it's operational requirements and support requirements.
So I would argue system management in HPC is a subset of system management in general. And system management for enterprise or for organizations as a whole is one of the #1 priorities for all of the main vendors. So Microsoft, IBM, they're all putting billions of dollars into this, whether it's autonomic computing or our dynamic systems initiative. All that stuff is key, and if we don't solve it in general, then the whole industry is going to go splat. So in this case, I think the scientific community can ride the tailcoats of the general community. Just as the grid community has moved over to web services, realizing that that's a 10 times bigger market in the enterprise that's doing the same thing, I think the same argument can be made here. We're out of time, so I think let's declare victory, and you can all go on to the next thing. Thank you very much for coming.